In this lecture, we are going to talk about a compressible flow solver which is called rhoCentralFoam. This particular solver can solve a compressible flow, and it requires that the mesh is uniform or there is no abrupt change of mesh resolution as we see in meshes which are generated using snappy hex mesh. These particular solvers are called density based solvers. Here all the equations are solved in the conservative form. In this particular lecture, our focus will be governing equations, the turbulence modeling that are present in rhoCentralFoam, the numerical methods, and some miscellaneous solver setting. In this lecture, we are not going to do any real simulation. We'll just talk about the overall rhoCentralFoam, and then in the next lecture, we are going to do some real simulations. This is the continuity equation. Here the variable is this rho, which is called density. Similarly, this is the momentum equation. Here the conservative property is this, which is called the momentum. Note that the velocity is not the conservative property, it's the momentum. Similarly, in case of energy equation, the conservative property is this E, which is called the total energy. And these all can be clubbed into the flux term. These are called the flux terms, or we can just keep this in the flux term and take these two as the source terms. Similarly, for the momentum equation, this is the flux term and this is the source term. Remember that when viscosity is 0, this term is 0 and we only have this term here. Now, in order to close this particular equations, you can see that you have in the mass conservation, you have rho. In the momentum conservation, you have rho u, rho v, rho w, and in energy, you have E. So you have one variable, 2, 3, 4, 5. Along with this, you also have pressure. Pressure is another variable. In order to close this, we use this equation state, another equation which links that how pressure is related to density and energy. This is the perfect gas assumption. There are various other kinds of equations of state as well that you can use according to your simulation. In particular, this rhoCentralFoam, it uses this particular scheme. It is a shock capturing scheme, and this is TVD scheme as well, which is called total variation diminishing, and the time integration is explicit. That means whatever variable update we are going to do, it depends upon all the variables from the previous time step times delta t or whatever. This is called the explicit time integration, and clearly that, as I explained before, that it is suitable for compressible flow with shocks. Now, even though this particular scheme is not particularly used with turbulence, but it supports these turbulence models. There is option and you can also use, but it is not recommended to use a turbulence model with rhoCentralFoam solver. You can enable these models using turbulence properties, as you have seen in various other tutorials that are there in our YouTube channel. And this is how you can write a turbulence property dictionary. Here, if this is a laminar simulation, you can write laminar, and if this is a Reynolds averaged simulation, then you used RAS, and then you have to define that what kind of Reynolds averaged simulation is this. If this is k omega SST, you can use k omega SST. If you have k epsilon, you have to write k epsilon, etc. And you can also pass the coefficients which are there for the particular model. You can also change them, but it is not recommended to change unless you are doing some kind of academic research on the variation of these coefficients and the effect on the results. Since we are using an explicit time integration, therefore we have stability constraints. Turbulence models works well with implicit time stepping, and since there is numerical dissipation, it affects the accuracy of the Reynolds simulation. And with this, you cannot use LES or DES kind of turbulence models. This particular solver is recommended for supersonic or hypersonic flows, but for supersonic or hypersonic flows, you have sonic-foam, another solver that is present in OpenFOAM, and you can use this for compressible jets and nozzles. And this particular solver is not recommended for subsonic flows. As said before, you cannot have LES or DES kind of simulations using this particular solver. And if it is high viscosity or low speed flow, in that case, if it is low speed, clearly this is going to be incompressible, and for incompressible flow you cannot use this particular solver. Then let's talk a little bit about thermodynamic model. Since we are going to use an equation of state, which is P is equal to gamma minus 1 rho times E. This also requires some other properties, that how E will be calculated and how different variables are related to each other. For that, you need a thermodynamic model. You also need the equation of state, the energy model, how energy is related to temperature, and the transport properties. So basically, these thermodynamic properties are the closure for the rhoCentralFoam, or in general, it is the closure for all kinds of models which requires an equation of state. Let's see how we can do that. In a thermotype dictionary, you can pass all kinds of values which tells you that how different variables are linked. Let's talk about them one by one. This tells you that how the enthalpy and compressibility are linked. Compressibility affects the speed of sound, and from the speed of sound your time steps are affected, and from the equation state you will get that how pressure is related to two other variables. In this case, this is the perfect guess. From this you can also derive this particular equation depending upon this particular relation, that how this is defined, how this thermo is defined. Thermo is H constant, that means the energy can be Cv times T, and the enthalpy is Cp times T. If these two are constant, then from this particular relation you can get the energy which will be used in the equation state. And then this particular sensible internal energy means the small e is the variable for which the particular solver, this rhoCentralFoam, is going to solve for E. You can also have this as H, then in that case it is going to solve for H, which is the enthalpy. You can also have transport properties as variable. If it is constant, in that case you will have this conductivity as well as this nu, which is the viscosity, as constant, and it is not affected by temperature. This is all the relations which tells you that how E is going to be evaluated, how H is going to be evaluated. This is the total energy, this is the compressibility, and from this thermotype you are going to get all these relations, how they are calculated as a whole. In the discretization, you should define all these things which is there in all kinds of other solvers as well. In addition to these, you should also have a flux scheme in rhoCentralFoam solver. This particular flux scheme is the only one which is used for all the flux calculation for momentum, continuity, as well as for energy equation. These are the options. If you want to change any time stepping, you can have these. You can have for Divergence scheme as well, you can have all these, and for Laplacian scheme as well, you can have all these. You can have Gauss linear corrected as well as Gauss linear limited. These are all other options which we can try when we are doing the actual simulation. In summary, the rhoCentralFoam is ideal for shock dominated flows only. If you want to do something else like a general compressible flow in which there is temperature variation or something like that, and there is no shock that is going to be there, then it is recommended to use rho pimple foam. And if the flow is supersonic or hypersonic, then in that case you should use sonic foam. And both these solvers can handle abrupt change of resolution, the meshes that we get from snappy hex mesh. In case of turbulence modeling, it is limited to runs, but in case of these two, rhoPimpleFoam and SonicFoam, you can have runs as well as LES and DES. The integration is only explicit. We'll see that whether the other time stepping works or not. Then you can pass various properties that are required using the thermo properties and the transfer models. We can configure all these in the dictionary. Apart from this, you should note that in case of compressible flow, you should have the pressure, temperature, velocity of the actual flow. Why I am saying this? Because in case of incompressible flow, you can have the velocity set according to the Reynolds number of the flow. You can change the dimension of the problem. For example, my length scale, I changed from 1 to 0.1 and just maintain the Reynolds number, and still I'll get the results which are similar. But in case of the compressible flow, if I change the dimension, then my velocity will change, and if my velocity is going to change, then my Mach number is going to change, and various other correlated variables are there which is hard to handle. It is always recommended in case of compressible flow that you use the actual dimension of the geometry, actual velocity of the flow to simulate the compressible flows. That's it for this particular lecture. If you like the content of our channel, then please like, share and subscribe. Thank you.